Hello Year 11 and welcome to another video with Dr. Beck. This video is going to be on the topic of um, physics, looking at motion. This is the first video in a series, and for this video you will need your book, you will need a pen, you will need also a pencil, a ruler, you may also need a rubber. Please also have a calculator. And if you also have some graph paper, that would be very, very useful. If you haven't got those things, please pause the video and come back when you've gathered those things together. Okay, this morning then, could you please in your book write down today's title and the objective, date and keywords, please. Pause the video when you're ready, come back when you finish writing those things. Okay, so today we are going to just do a bit of a review of scalar and vector quantities. This is something we have seen in the past, but we're going to do a review. In particular, we're going to be looking today at an important thing called displacement. But we're going to learn about scalar and vector quantities so that we can identify some examples and then calculate displacement using scale diagrams. And along the way, we're going to refresh our memory about the word scalar and vector and distance and displacement. We are going to be using a diagram, and we are going to be using scale diagrams. So first of all, in science, we often need to measure things. If we can't measure something, we can't look at the effects of something else on that thing. We call things that we can measure physical quantities. Okay, and there are two types of physical quantities. There are some quantities, for example mass, which just has a size. We have a unit and we have a number, 5 kilograms. That's it. There is no other part of that quantity we need. Other things, however, in physics we say they have both a size and a direction. For example, a force. Now in the previous module you were looking at forces and looking at balanced and unbalanced forces, and we were using arrows. Now the arrows weren't just there to look pretty, they were showing the direction the forces were acting in, and we'd normally label the diagram with a number and then the units, which are newtons for force. So we say then that scalar quantities have a size, but they do not have a particular direction. They have no direction. And the other type of quantity then is what we call a vector quantity. Vector quantities have both a size and a direction. If you think any of that is useful to write down, please take a second to do that and come back when you're ready. Okay. So what we're going to do is just sort some of these quantities, some of these physical quantities into two groups. We have got 9 quantities, either scalar or vector. Remember at the top it says scalar quantities have a size, and we can also use this word magnitude only, and they have no direction. However, vector quantities have both size and direction. So please, in your book, can you make 2 columns, one headed scalar and the other one headed vector? And then below, could you write at least the numbers for each one in each appropriate column, or even better, to help with revision, the actual name of the physical quantity, for example, mass. I'm going to give you 2 minutes to do that. However, when you're ready, please come back once you have paused the video. Okay, let's go through these one by one. The first one, number 1, is mass. As we've already discovered, this has just a size, just a magnitude, and therefore is a scalar quantity. Distance is the same. It has a size, for instance 2 meters, but it's got no particular direction. Acceleration is a vector quantity. As we discovered in the previous module, we can have positive or negative acceleration depending on the forces acting. For speed, We'll come on to speed in the next video, but speed is a scalar quantity. We can move at 2 meters per second, 4 miles per hour, in no particular direction. 5, velocity. We should have recognized that this is another vector quantity. The velocity is a vector quantity. 6, energy is scalar. Time. You can measure time, but it has no particular direction. It is a scalar quantity. Power is also a scalar quantity. And as I've already discussed in this video, force, we need to give both its size, its magnitude, and its direction. So that is therefore a vector quantity. Okay, use your purple pen, please, to just correct or check your work. If you've got them all right, give yourself a pat on the back, and we will move on when you're ready. Okay, so here we're going to look at something we call displacement. We've already discussed what we mean by distance. We should have an idea what we mean by distance. We're going to introduce this other idea of something called displacement and displacement vectors. So the second part of our lesson is from this to work out the displacement of an object from its starting position. So here we have a man, he's walking, he's going to walk 10 kilometers north, and there he goes, and then 10 kilometers east, and we can show that with these arrows in our diagram. We are going to now add and replace those two movements with this displacement vector. Now the distance he has traveled is simply 10 kilometers plus 10 kilometers. How much is that? Yeah, 20 kilometers. However, his displacement is not the same. He has moved in those two directions and has come to this point. And this is now his displacement from the starting position. So what is his displacement? It's quite tricky, but see if you can work out how far that displacement is. Have a go, pause the video, come back when you think you are ready. Okay, now notice we're using north and east. That should give you a hint that we're using directions at a right angle. We can therefore use Pythagoras. So, mathematicians amongst you, we use 10 squared plus 10 squared, and we add those together, and then using Pythagoras' rule, we take the square root of that sum. So the square root of 200 gives us 14.1 kilometers. So here is the length of that displacement vector, and the direction is in that northeast direction. So again, this is a thing we do in physics. Our displacement vector has two components. Its size, here it's 14.1 kilometers, and its direction, northeast. Notice the distance was 20 kilometers, however his displacement is 14.1 kilometers northeast. Let's have another go. First of all, let's just refresh our memory. The distance is a scalar quantity. It refers to how much ground an object has covered during its motion, the total distance of that motion. However, the displacement is a vector quantity, and it's the straight line distance between where an object started and where it finished. It refers to how far out of place an object is. It is the object's overall change of position or change in position. If you think that's important, you want to write that down, please pause the video and come back when you're ready. So let's have a look at an example. Dr. Beck walks 4 meters east, 2 meters south, 2 meters west, and finally 2 meters north. What is my total distance traveled? What is my total displacement? Maybe you've got an answer. Maybe you figured it out. However, I'm going to make my life a little bit easier. I'm going to draw a diagram, which is part of what today's lesson is all about. So here's my diagram. 4 meters east, using our compass points. 2 meters south, 2 meters west, and finally 2 meters north. Questions. What is my total distance covered? Now, distance is a scalar quantity. It refers to how much ground an object, in this case Dr. Beck, has covered during motion. So, shout out, what is the total distance? Good. Hopefully you recognize we simply add all these numbers together. 4 plus 2 plus 4 plus 2 is 12 meters. However, what is my total displacement? How far have I moved from my starting position? Shout it out. Well, my displacement is actually 0. I've done all that work, but I've come back to the beginning. My displacement is 0. Well, I don't know if you got that right. This is quite a tricky little subject. So here we can see another diagram just to show the difference between distance and displacement. So this person has walked around a path. He has covered quite a distance. However, he has been displaced by the distance shown by the black arrow here. The displacement here is much less than the total distance covered. Those two quantities are not the same magnitude. The distance does not have direction, displacement does. Okay, we're going to do a little practice. I'm going to show an example, then you can have a go at one yourself. Now we're going to use scale diagrams. So if you have equipment, as I asked you at the beginning of the lesson, at the beginning of the video, please make sure you have it in front of it now. Often in physics, it's really useful to draw scale diagrams. Okay. Now in an exam, should we sit exams, there will always be some graph paper to help you to do that. Now the tricky bit is to work out an appropriate scale, and that's something that students often find difficult. But for now, we're going to try a worked example. In this picture, you can see that there are 3 parts to this journey. There is a component A, there is a component B, and a component C. And the resultant vector is this, as shown by the thicker purple line. And using this scale, you can see that the person has come up with an answer of 50 meters. And we're going to try something very similar here. So if you have graph paper, you can follow this with me and draw as we're going along. So here is our introduction. You must draw a diagram for each quantity you work out. Okay, it's going to be much easier if you draw accurate with a pencil and a ruler, using an appropriate scale and using graph paper. You must label any of your arrows in pen, and your final answer for either displacement or for distance must be complete. So for distance, just the size, and for displacement, the size and the direction. We're going to use this compass to help you. Okay, let's go on a journey, and you can follow along using graph paper if you have it. If not, use a ruler and pencil as accurate as you can in your book. So let's say somebody sets off and she walks 80 meters north. Okay, so 80 meters, we can't draw that in a book. We'll have to scale it back. So I suggest a length of 8 centimeters would be an appropriate scale to use, where 1 centimeter is the equivalent of 10 meters. So if you haven't already done that, do that now, please. Draw an arrow 8 centimeters long, pointing upwards on the sheet to represent a movement north. Next, she turns right and she travels in an easterly direction for 50 meters. So using our scale, how long should that line be? Yeah, that's right, 5 centimeters line. Well done. So 5 centimeters line, please, to the right from the end of the first arrow. Now she's going to turn right again, and by turning right, she's now going to move south. And the distance is on the screen. She has moved now 10 meters south. So using our scale, how long should that line be? Yeah, that's right, 1 centimeter. Well done. Final part of this journey, she is now going to turn left and she is going to move 70 meters eastward. Okay, how long should that line be using our scale? Yeah, that's right, 7 centimeters. If you need to pause the video to complete your drawing, please do that and then return when you're ready. Now, the first question is, what is a total distance traveled? Write that down, please. Total distance traveled is? Right, well, the total distance is the total sum of those parts where she is in motion. The total motion, the total distance she has traveled is 80 plus 50, which is 130, plus 10, which is 140, plus 70. So the total distance that she has traveled is 210 meters. Well done if you got that right. Next question, however, what is her total displacement? Now I'm going to give you a couple of minutes to work that out. Now this is where your scale diagram becomes really useful. Two ways you can do this. Either you can measure the distance from her start point, bottom left, to the end of the fourth arrow. And if your scale diagram is accurate, you can simply then use that length and scale it up to give an answer. Otherwise, you can use Pythagoras, but it's not as easy as it looks at first glance. However, whichever way you choose, give yourself a few minutes and come back when you're ready. Okay, let's have a look at the mathematical way to do this, and then we can confirm that with a scale measurement. Okay, her total movement to the right in an eastward direction, we're simply going to add up those numbers. 50 and 70 gives us an eastward component of this of 120 meters. Now she traveled 80 meters north, but then 10 meters south. So that total component is actually 80 take away 10, which is 70 meters. So we can now use this right angle to make a right angle triangle, and then use Pythagoras' theorem to calculate the total displacement from her starting point. So here we go. Here's the line we're looking for. And here's the equation that we can use. Okay, x is the length of the green line, the diagonal line, and then we're squaring the other two sides to give us x squared, which can then square root. If we do all that, we come up with an answer of 139 meters approximately. Notice that's a lot less than her total distance. Displacement is the distance traveled in a particular direction from that starting point. And just double check. If you've drawn an accurate answer, you can measure this distance with a ruler and then scale back up using our scale of 1 centimeter is the equivalent of 10 meters. So if you've drawn this accurately, you should be measuring 13.9 centimeters. Well done if you got that all right. Okay, we're going to have one more practice, one more final practice, and we're going to calculate a displacement of an object. So, I beg your pardon. So first of all, yes, I forgot to mention that the fact that we have a direction. Yes, so 139 meters in a northeast direction. Now we could measure this angle, okay, and in a higher paper we might be asked to do that, okay, and that will be the angle from north. So we could actually measure this or work it out using SOHCAHTOA, but simply for trilogy science, northeast will be sufficient. All right, let's move on. So let's have a go at this. Again, for the best possible outcome, you should be using accurate drawings, using a pencil and a ruler, using graph paper, rubbing things out if you need to, and using the points of the compass shown top right. So have a go please at this example. I'm going to read it out to you, then you can have a go for a few minutes. A man walks around a park, first walking north for 80 meters, then turning right and walking for 50 meters. He then turns right again, heading south, and after 50 meters takes a right turn and continues for 50 meters. How far is he away from his start point now? So that final question, what is his total displacement from his start point? Have a go at this. Come back when you're ready. Okay, hopefully you didn't find that too difficult. You use an appropriate scale. Let's have a look at this journey. So once again, 80 meters north, 50 meters having turned right to the east, 50 meters south, 50 meters to the west, he turned right. The total displacement then is simply just 30 meters north. Well done if you got that. Now the total distance he's travelled there is well over 200 meters, 230 meters, but ultimately he's come back almost to his starting position, just 30 meters north of where he started. Okay, so today we've been learning about scalar and vector quantities. We've learned about scalar and vector quantities. We've reviewed what we've previously learned in our other topic, and we've then been able to identify some examples, and then we focused on calculating displacement using scale diagrams. If there's anything you need to review, and that's up to you. You can use the video and pause it, whatever you like, practicing those accurate drawings of scale diagrams. However, for now, that's all. Thank you very much indeed. See you next time.